Welcome to the pod, Cultivating Innovation, one batch at a time. This is biomanufacturing and fermentation technology.
Welcome back to the deep dive, where we take your source material and really extract the essential, actionable insights fast. Today, we are diving deep into the engine room of bioprocessing, the industrial design of cell culture media. I mean, for decades, right, the industry pretty much treated media as just high-performance food.
Exactly, just food. The critical input you optimize for one thing and one thing only, getting the maximum possible titer or cell growth.
But that's all changing now.
It's rapidly becoming a relic. Our sources, they consistently hammer home that media is now functioning as a really sophisticated upstream programming layer. That traditional mindset where, upstream formulation was done in a total vacuum from downstream purification. One paper we read called it, and I'm quoting here, no longer defensible.
No longer defensible. So those two worlds are finally merging.
By necessity, yeah.
So let's unpack that integration. Our mission for you, the listener, is to understand how the chemical composition of the broth isn't just a biological concern anymore. It's an engineering lever.
A powerful one.
We're talking about intentionally designing the broth to control things like impurity generation, product separability, overall cost, and total process robustness.
It's a huge shift away from just optimizing for maximum yield. The new goal is the best total process objective.
And what's driving this? What makes this possible now?
It's really convergence of tools. On one hand, you have this revolution in analytical depth, especially LC-MS for profiling impurities. And on the other, you have computational intelligence.
And you mentioned something about fundamental chemistry, too.
Right. We're also seeing the mechanistic application of, basic chemistry bringing concepts like the Hofmeister series out of the textbook and right onto the plant floor.
This sounds less like self-eating and more like chemical warfare against future bottlenecks.
That's exactly the right way to think about it. The moment those cells start growing, the media composition is profoundly influencing not just how much product you make, but the identity and the abundance of things like host cell proteins, proteases, all the junk that floods your recovery process.
So the media is literally an impurity and separability programming layer.
That's the term, yeah.
And this is where it gets really interesting for me. The analytical shift that lets this programming happen. I mean, historically, we've relied on aggregate measurements, right? Like ELISA.
Yeah. Which basically tells you the total amount of HCPs. If the number was high, you just told the downstream team to, work harder.
But now we have granularity.
We do. ELISA is still critical for release, don't get me wrong, but it only gives you that one aggregate number. LC-MS, that's liquid chromatography mass spectrometry, has matured into a practical, orthogonal tool that gives you species-level resolution.
So it moves the conversation from we have too many impurities
to something much more specific, to we have too much of species X, and its PI matches our target product, which makes clearing it nearly impossible.
We're talking about real forensic detail.
Yeah.
How detailed can this actually get?
Oh, incredibly specific. A recent LC-MS workflow we saw, one developed for routine process support, showed they could identify and quantify well over 1,000 individual HCPs.
1,000.
1,000, including the 20 highest risk species that are all over the public literature. And this is directly from the clarified cell culture fluid. It's a paradigm shift.
So you're not just counting the whole population, you're identifying the specific problematic individuals.
That's the key. Because like you said, downstream failure isn't usually caused by the sheer quantity of HCPs. It's almost always dominated by a small handful of these persistent species that share properties with your target molecule.
The ones that cause coelution risks.
Exactly. You could have a low overall HCP number, but if the ones that are left are really sticky or co-purify easily, you still have a massive problem on your hands.
So what's the new workflow? How does this work in practice?
It's a three-step process, really. First, you use LC-MS to profile the harvest fluid. Get your map of the impurity universe.
Step 1.
Step 2, you classify the high-risk species based on their known properties, PI, molecular weight, maybe known protease activity. And then step 3, you go back upstream and strategically change the media to suppress those specific contaminants.
You're targeting the cell's physiology that causes the release in the first place, not just cleaning up the mess later.
You got it. You're programming the impurity profile right from the start.
That has to have massive cost implications. Do you have a concrete example of this working in the real world?
We do. Look at recombinant insulin production in Escherichia coli. Traditionally, E. coli processes use these complex nitrogen sources. They're cheap, but they introduce huge analytical variability and really high impurity loads.
Okay.
By shifting to a guided media design, using that LCMS data to suppress specific persistent species, they were able to cut those key impurities by 30 to 40%.
40% reduction in the impurity workload. What does that actually mean for the bottom line?
It fundamentally changes the economics downstream. The affinity chromatography steps were cleaner, so they achieved residual HCP levels of less than 100 parts per million.
Wow.
And this was in high-density fed batch runs from just last year. It meant fewer polishing steps, less resin cycling, lower buffer usage, and much faster batch release times. You cut costs, you cut time, and you boost confidence in your regulatory filing, all because you started cleaner.
And it's not just proteins, right? You mentioned other things, what our sources call DSP stressors.
Yes, absolutely. Especially when you get into microbial and fungal fermentation. We're talking about exudates and polysaccharides.
The slimy secret ingredients that gum up the works.
Precisely. They're the major drivers of viscosity and filterability. In fungal citric acid fermentations with Aspergillus niger, for instance, they designed media specifically to minimize the production of these XL polysaccharides.
And what happened?
That one optimization reduced the broth viscosity by 20 to 25%.
25% less sludge to push through the filters. That's huge.
It translates directly into operational efficiency. That media change prevented 15 to 20% earlier filter breakthroughs. In a continuous process, that's an enormous gain. So it's not just static screening anymore. Media development is now about life cycle monitoring of these trajectories, often tracked live with PADI approaches.
Okay, so if we're tracking this stuff live with PADI, that puts incredible pressure on the initial broth chemistry, right? We're moving way beyond just controlling pH.
That's the perfect segue. Downstream separations, binding capacity, elution selectivity, precipitation, they're all powerfully governed by the broth's physical chemistry. We're talking ionic strength, buffering species, all those subtle ion-protein interactions.
So mechanistic selection. If you know you're using ion exchange chromatography later, you should be choosing your media salts now with that in mind.
With explicit awareness of how they will support that mechanism later, yes.
And this is where we see chemists pulling out their old physical chemistry textbooks, applying guidance from the Hofmeister series.
Exactly. It's not just dumping in sodium chloride anymore. We are deliberately choosing ions to push a protein toward either stability, which is what cosmetopes do, or toward aggregation, which is what chaotropes do. It's highly predictive.
So you're using ion selection as a subtle chemical lever to condition how proteins will behave 3 steps down the line. Arginine is a great example of this, isn't it?
It's a perfect example of that dual value, quality and separability. Arginine is often used in elution buffers to reduce HCPs by preventing aggregation. But the mechanistic work shows that the choice of counter-ion like chloride versus sulfate, that choice, impacts aggregation suppression in a way that is totally consistent with Hofmeister ordering.
The counter-ion matters just as much. Well, using salt isn't good enough anymore. You need the right salt.
The right salt at the right concentration, often to preempt aggregation entirely. We saw a great application of this in succinic acid recovery from Corynebacterium glutamicum. By using Hofmeister-guided arginine hydrochloride in the fermentation buffers, they successfully suppressed protein aggregation right from the start.
And the downstream impact.
It was huge. That suppression translated into much better ion exchange performance. They boosted yields up to the 70 to 80% range, all while keeping HCPs low. The cosmotropic ions conditioned the input material to make the column perform better.
That is true integration. Now let's talk phosphates. They're essential for cells, but they're also potent buffers. Does managing that upstream affect your downstream tech choices?
It absolutely does, especially if you plan on using steps like aqueous two-phase systems, or ATPS, which are incredibly sensitive to salt concentration and pH.
Right, ATPS is that liquid extraction between 2 polymer phases.
Correct. And if your upstream media has a high phosphate buffer capacity, you have to spend a ton of time and money conditioning that buffer before you can even start the ATPS separation. But our sources show that using phosphate-limited media in lactic acid fermentations, well, it facilitated the subsequent ATPS step beautifully. By controlling that one input, they hit a partitioning efficiency of 80 to 90%.
So they essentially removed an entire intermediate conditioning step.
They did. It really crystallizes the message. Every single ingredient is a potential strategic lever. And there's a flip side to this, too.
Which is?
Media that induces extreme pH or high osmolarity that heightens the risk of cell lysis. When cells lyse early, they dump all their proteases and HCPs into the broth, undoing all your careful work.
All right, so that requires active mitigation, tracked not just by viability, but by looking for those stress indicators with LCMS in real time.
Exactly.
Let's shift gears and look at how media choices can determine the very starting point of the entire downstream process by affecting product localization, where the product actually ends up.
Right, because media modulates the cell's internal environment and its secretion capacity. And that's critical because it determines whether your process starts with simple cell removal because the product is outside, or with complex, costly cell disruption and refolding because the product is stuck inside.
And disruption and refolding are not just expensive, they are a huge risk for product loss and aggregation. Can media design actually help you bypass that whole mess?
Absolutely. Take paraplasmic antibody fragments in E. coli. They're often trapped in the paraplasm. But by supplementing the media with a high concentration of osmolytes, like sorbitol,
Osmolytes, okay.
usually between 0.5 and 1 molar, they were able to promote secretion into the culture broth. They got 60 to 70% secretion.
60 to 70%. That's a huge win.
It meant they could bypass disruption and refolding almost entirely. The cost savings and recovery were estimated at about 20% overall.
But there's always a trade-off, isn't there?
Always. Pushing cells toward hyperosmotic conditions in mammalian systems can introduce other risks, like reduced viability or unintended changes to post-translational modifications, like glycosylation. You solve one problem, you have to monitor for 3 others.
And that balancing act becomes incredibly tight when we talk about fragile advanced modalities, viral vectors, for instance.
The stakes are definitely higher there. Viral vectors are inherently shear-sensitive particles. For these, media decisions that simplify clarification and reduce damaging impurities often deliver a much better outcome than trying to fix things later with complex DSP.
So better to prevent the damage than try to repair it.
Fundamentally. For example, using a low-impurity media for viral vectors produced in HEK 293 derivatives simplified the clarification steps, it minimized mechanical stress, and it improved overall yields by a substantial 25%.
A quarter more product, just from upstream discipline.
It proves the philosophy of process harmony. And this drive toward integration isn't just about efficiency, it's being mandated by external factors, too.
Like what?
Compliance and traceability. For example, the push for defined media. Defined media inherently reduces process variability studies show by 30 to 40% in CHO cultures, which is critical for root cause analysis and robust change control.
And what about sustainability?
That's the other big one. Regulatory requirements are now directly impacting formulation. You have the European Commission's CSRD and ESRS standards coming into effect for the 2024 financial year reports.
Which means?
It means if you're a large pharma company, you now have to quantify and report on your supply chain impact. This creates huge commercial pressure to favor media with traceable inputs and a low carbon footprint. You can't just throw in complex hydrolysates with opaque supply chains anymore.
So we have the analytics with LCMS, the chemistry with Hofmeister, the compliance drivers, and finally the intelligence layer, AI and hybrid modeling.
Right. The role of AI here is to rapidly accelerate that upstream-downstream integration loop. Traditional modeling is just too slow. AI and hybrid models can handle the massive data sets from LCMS impurity profiling and complex media screening.
And they allow for rapid prediction of optimal conditions that would take years to find with traditional experiments.
Precisely. A 2025 downstream optimization case study used AI hybrid models to optimize ion exchange chromatography under incredibly tight purity constraints. They reported a final predicted yield of 82%.
And how did that compare?
It was versus 78% achieved by the best mechanistic model under the same constraints.
For 4% yield improvement sounds minor, but what does that 4% actually mean when you're talking about a multi-ton biologic?
That 4% translates directly into millions in cost savings per year, and it significantly accelerates the timeline to hit volume targets. It really reinforces the core philosophy we started with. Define your upstream media not by best titer, but by the best total process objective.
Okay, let's bring it all together. This deep dive has shown us that media design is no longer just a biological input. It's strategic process conditioning.
It's a strategic bridge between cultivation and purification built on 3 pillars: quantification from LCMS, mechanistic chemistry like Hofmeister, and predictive intelligence from AI. Upstream and downstream are now just inextricably linked.
And for you, the listener, The benefit of adopting this product-centric paradigm seems clear. Process harmony. It streamlines operations, gives you purer, more recoverable outputs with a lower cost of goods.
You get a process that's smarter, faster to scale, and critically easier to defend to regulators.
Which leaves us with a final, provocative thought.
If advanced analytics and AI can now predict and even eliminate traditional purification steps just by engineering the broth itself, what is the ultimate trade-off? The trade-off between maximizing that immediate process efficiency and maintaining the necessary complexity to ensure a product's long-term robustness against future unexpected impurity threats that maybe the AI hasn't even modeled yet.
Something to chew on as you consider just how lean you can truly make your next bioprocess design.
How do we solve the valley of death in biomanufacturing? It starts with better data and more robust fermentation technology. Join us on Biomanufacturing and Fermentation Technology by Prasad Ornala for our upcoming series featuring lead researchers and process engineers. We're discussing everything from bioreactor design to downstream processing, DSP efficiency. Follow us now to join the conversation on the technical frontiers of biology.